In this course, we learn various symbolic or formula techniques for solving ODEs, that is, ordinary differential equations. For first-order equations, the three main types that we study are linear, separable, and exact. All of these, and other techniques as well, involve finding primitives or antiderivatives of functions using schemes that you learned in one-variable calculus. MATLAB is quite expert at both the integration schemes and numerous formula techniques, including the three I just mentioned, for solving first-order ODEs. The relevant MATLAB command for doing so is Dsolve. In this video, we will learn how to use Dsolve in order to solve first-order ODEs, associated initial value problems, and then we'll learn how to graph the solutions that come out. So, for example, suppose you want to solve the following first-order ODE. Y prime plus 2t over 1 plus t squared y equals the quantity 1 over 1 plus t squared all squared. Well, you should recognize that as a prototypical first-order linear equation, an equation of the form y prime plus p of t y equals q of t. P is the quotient 2t over 1 plus t squared, and q is 1 over 1 plus t squared squared. Now, you learned a formula or recipe for solving equations like that, and the recipe actually gave you the general solution, which is y equals c times mu inverse plus mu inverse times the integral of mu q, where mu is e to the antiderivative of p. And so it involves two anti-differentiations. Now, the preferred MATLAB syntax for solving this equation, or an equation of this form, via Dsolve is as follows. You first type sims t, y, y of t. So we're declaring t, y, and y of t to be symbolic variables. And then here's the Dsolve command. Dsolve. First, the differential equation in this format. Diff of y plus, you have to put in the next term, and that's as follows. 2 times t divided by 1 plus t squared times y equals, and for this we use a double equal sign, and then I have to put in the last expression, q, 1 divided by 1 plus t squared squared. If you run this command, as we will momentarily, you obtain the same answer that you get by applying the linear equation technique mentioned above. Namely, what comes out is y equals c over 1 plus t squared plus 1 over 1 plus t squared times the arctangent of t. If in addition you have an initial value problem, you specify that, for example, suppose that y of 0 equals 1, then if you put t equals 0 in the right-hand side of this equation, you see that everything goes out except just the c, and so in this case c will be equal to 1. Okay, so the MATLAB syntax for the initial value problem is, as before, Dsolve put in the exact same thing that we did above. But you also have to specify the initial condition, and you do that by writing y of 0 double equal 1. And in fact, it would be good to name that for the following reason. The reason is I want to use the output to actually graph the solution. I also note that on the preceding page I forgot to include the closing right parentheses for the first Dsolve command. So let's correct both of those by reissuing the command together with the initial condition with a name. So I'll call it solution, S-O-L-N. This will be Dsolve. So I'm putting in the differential equation once again. Diff y plus 2t divided by 1 plus t squared times y equals the quantity 1 over 1 plus t squared squared. Now the initial condition. I could suppress the output by putting a semicolon there, but if I wanted to see what actual solution function comes out, I would not include the semicolon. Now, if you want to graph the solution, all you have to do is type EasyPlot solution. And we'll do that in a moment, and you get a graph of the solution to the initial value problem. Now, MATLAB is not omniscient. Various things can happen less desirable than an explicit solution emerging as occurred above. And here are some examples in increasing order of complexity. So the first thing has to do with the fact that you could get an implicit solution. MATLAB may only be able to find an answer in implicit form. In fact, here is an example. 2x plus 1 dx minus 3y squared minus 2y dy equals 0. So there's a first order equation which is actually separable and as well as exact. And if you solve it, it doesn't take you long to see that the solution is x squared plus x minus y cubed plus y squared equals constant, which is the exact same curve as we saw in the contour plotting video. So you know how to plot that, and I won't give you the commands. The next thing that can happen is MATLAB can't find primitives. That is, all of our techniques for solving differential equations involve finding primitives or antiderivatives, and sometimes MATLAB just can't perform the integration. We'll see an example momentarily where MATLAB reports its answer in terms of an unevaluated antiderivative. Another thing that can happen is MATLAB gives up. I'll also see an example in a moment where MATLAB reports that it just can't solve the equation. For such equations, one has to deploy other methods, either graphical techniques, sometimes called geometric techniques. And for that, one has the commands mesh, grid, and quiver. And we'll see those in a future video on graphical techniques, and one could also use numerical techniques using the MATLAB command ODE45, and we'll also see how to do that in a future video. And then the last thing that could happen, the worst thing in some sense, is that MATLAB makes a mistake. Well, it's extraordinarily rare, but it can happen. And you can see an example on page 67 of the Dune book. So differential equations with MATLAB, page 67. And I will replicate that momentarily. Now we will illustrate some of the MATLAB commands I've been describing by actually running them in a MATLAB window. So first, the basic example of a linear differential equation, the equation that we discussed. I declared the symbolic variables, and I used Dsolve on y prime plus 2t over 1 plus t squared y equals 1 over 1 plus t squared squared. So if we run that, it takes a second, but it actually solves it. But the solution is in the MATLAB window. So let's look there. There it is. Just what we said, constant over 1 plus t squared plus arctangent over 1 plus t squared. Now back to the editor. And now let's do an initial value problem. We again solve the same differential equation, but with the initial condition y of 0 equal 1. And if we run that and open up the MATLAB window again, we see 1 over 1 plus t squared plus the arctangent of t over 1 plus t squared, which is, as we know, the solution to the initial value problem. Okay, now let's get its graph. Notice I called it solution, or SOLN, as I did in the earlier page. And now I just issue the command EasyPlot solution. Let's see what happens. There's the solution. Notice it's titled, and that's what the function looks like on the interval minus, a little bit bigger than -2 up to 6 roughly. EasyPlot chose that as the interval of definition. But as usual, you can alter the interval over which the solution is graphed by issuing the command EasyPlot solution, but with a specified interval for any particular choice of A and B. Next, let's see how to plot a family of solutions. Basically, this time I called it solution A. It's a solution of the differential equation with y of 0 equal to A. And then I drew the solution curves as A varied from -3 to 3 with step size 1. So there's a little for loop that sets that up. I titled the resulting graph and labeled the axes. And let's see, notice I set up a new figure. If we run it, there's all the graphs. Nice picture. Right, so there's 7 solution curves to the differential equation with 7 different initial values. Okay, now let's go further in this and look at the case where MATLAB solution is an implicit one. So this is the example that I described earlier. Notice I declared symbolic variables again. I'm using x instead of t now. And there's the differential equation, same one I specified before, 2x plus 1 minus quantity 3y squared minus 2y, y prime equals 0. I claimed it came out with an implicit solution. Let's see. So it thinks a little bit longer maybe than it did the last time. And if you look in MATLAB, it tells you, warning, explicit solution could not be found. An implicit solution is returned. And there he is. This is MATLAB's way of saying, it does it in terms of z instead of y, but it's y cubed minus y squared minus x squared minus x equal constant. Exactly the family of implicitly valued functions that I said would come out, and which we did discuss and graph in the contour plotting video. Okay, so that can happen. You could have implicit solutions. You can also have the case where MATLAB just can't do the anti-differentiation. So look at this problem now. Y prime equal e to the minus y plus y. Clearly separable. So what happens if we try to do that? MATLAB grinds away and tells you that the answer is in terms of an integral that it can't do, right? The integral of e to the y over y, e to the y plus 1. That's MATLAB's way of telling you that it can't do that integral. The answer is that integral minus t minus a constant equals 0. This here is a constant solution, which is actually a complex number. Okay, let's go back. So MATLAB couldn't anti-differentiate. This example is also discussed on page 66 of the MATLAB book. Here's an example where MATLAB gives up. So I'm solving y prime plus the square root of y equals t. Let's run that. And MATLAB grinds again a little longer, and this time it tells you that an explicit solution could not be found, and its answer is, I can't give you anything useful. So this one stumps MATLAB completely, and MATLAB knows it's stumped. Can't solve that differential equation. And finally, an example in which MATLAB actually makes a mistake. This example is discussed on page 67 of the MATLAB book. It's y prime equal t squared plus y squared, y of 0 equal 1, so it's an initial value problem. And I tried to use EasyPlot. I entitled it Oops, and I changed the color because it didn't come out so well. Let's see what happens. So that's clearly not a solution. It's not a single valued function. It's kind of a mess. And as I say here, truth be known, the mistake is more in how EasyPlot interprets the output of Dsolve rather than inherently in Dsolve. In vast majority of cases, Dsolve works extremely well. You may not get an explicit solution. You may get an implicit one, or one in terms of antiderivatives that MATLAB can't evaluate, but generally it will get you a solution to your differential equation or initial value problem. It's a very powerful symbolic tool, and so Dsolve is highly recommended to you, and you should try lots of examples that you can find in the MATLAB book. You could also work Dsolve on some of the problems that are in the notes.